So now we move to new topic. Still extremal graph theory, but we will move to new topic, which is called regularity. Say regularity lemma. So many times so far, our quest here is that we want to find certain subgraph inside of given graph when certain conditions are met. So in Turan problems, so most of the condition is that when we have a graph G which has many edges, now we want to find some subgraph, specific subgraph inside of G. For this problem, one of the situation is that if we have a graph G, let's say we have graph G which is somewhat random. Okay, let's just say that we have a graph G which is P1, P2, P3 to PR. And then for each pair of this vertices here, we flip a coin and then we add an edge with probability say 1/2. And same here and same here and same here, here. Then in this random graph, this is some sort of random graph, R-partite random graph, where let's just say each part has sufficiently many vertices. Then we can actually show that with high probability, we can find any small R-partite graph H inside of G. We can find them. So our concern before is that for certain H we want to find inside of G, but if G is random graph, this is really easy task. So random implies that we can find any small subgraph in it. So one of the natural question is that why does this hold? Or maybe this condition, can we weaken it a bit? So random graph here, you can find this, but what if there is some weaker condition? So which is weaker than randomness? So such random graph satisfies certain condition, but not the other way around. But this property or condition is still strong enough to ensure that we can find any small subgraph in here. If we can find somewhat weaker notion than this, then we may be able to use this property in a more efficient way if this is weaker than randomness. If this kind of condition or property is called pseudo-randomness or quasi-randomness. So if we have some random object, then it satisfies certain good property P. And if there is some other property, say Q, which still implies lots of this property P, but which is weaker than this randomness. So let's say this is not necessarily true, but still it implies lots of other, maybe P1, some other property. Then we call this as some pseudo-random condition. So this is not a rigorously defined concept, but whenever we have certain condition which is implied from randomness, but it also implies lots of other good properties which comes from the randomness. So one of the such concept that we will learn is the regularity. So, I mean, more precisely, it's called epsilon regularity. So here, this epsilon is some number between 0 and 1. Let's say 0 and 1. So when we have a, let's define it. We have a graph G and two disjoint vertex set A and B. Then let's write E of AB. Sometimes we omit G if it is obvious. It's the number of edges of G between A and B. And and let's say density of G between A and B is we normalize this by the, maximum possible number of edges between A and B. So this is density between A and B. So we have, say, these 6 edges. 3 vertices here and 2 vertices here. Then maybe you have the 3 edges. Then 3 over 3 times 2 is 1/2. So which is density. So how dense is the graph between these two? How many edges are there? Or roughly you can, imagine this as you choose one random vertex here and you choose one random vertex here. And you compute the probability that there is an edge between them. Then that's, there are this many random choices, and this many choices actually yields an edge. So in this case, the probability that the random choice you can find the edge between is 1/2. So which is this density. And we can define that a pair, say AB, of disjoint sets of vertices is epsilon D regular in a graph G if the following holds. So for any subset A prime inside of A, B prime inside of B, of sizes, so A prime not too small. So epsilon is some number we fixed, and B prime is also not too small. Then for all such A prime and B prime, we know that the density between A prime and B prime is very close to D. So for our convenience, let's write that let's write it somewhere here. We write C equals A. Let's say A equals C plus B plus minus C. Instead, sometimes we want to bound this A from below and from above. So instead of writing this in full, let's write it this way. So in this case, this can be rewritten as D plus minus epsilon. So what it means is that when we have this A and B, and you have these edges, and if these edges are well distributed in some random way, if it's randomly distributed, Then, however you choose A prime and B prime, if it's well distributed or uniformly distributed, the number of edges between here, should have a similar distribution of the number of edges between this entire graph. So, or for other sets, we also expect that if the edges are well distributed or randomly distributed, we also expect the number of edges here has a similar distribution as number of edges here. So if they have the similar distribution, the density must be close. So for whatever small set A prime, B prime, or other A prime, B prime, as long as they are not too small, then their density is close to D. And closeness is measured by its epsilon. So if this holds, then we say this is epsilon D regular. So we say that also AB is epsilon regular if it is epsilon D regular for some real number D. Okay, let's not do this. Or let's define it this way. This is equivalent, but if it is epsilon D regular for D being the density between A and B. So then if that's true, then we say this is epsilon regular. And we say this AB is epsilon D plus regular pair if it is epsilon D prime regular with D prime at least D. So let's consider some examples and try to digest what it means. So again, you consider the graph G between A and B, and you have the density between these two. So there are many edges, and roughly D proportion. D is the density between these two. Then roughly D proportions of the pairs are edges. So if you randomly choose one vertex and randomly choose one vertex here, then the probability that there is an edge between them is D. And now so this is global density. And now you choose some set here, A prime, B prime, and then you want to consider the local density between these two sets. And then the local density is measured by counting the number of edges between them, and then you divide by size of A prime and size of B prime. That local density D of A prime and B prime is also close to the global density, as long as this is not too small. Of course, if you just take one vertex here, and A prime and B prime is just a pair of one vertex, then the density between these two is either 0 or 1. So even if you take a pure random graph, every vertex, every edge here is there with probability half, then for this case, its local density is either 0 or 1, so it's always far from half. So it's too much to expect that this really small local density is also close to be the global density. That's why we put the lower bound on the size of A prime and B prime. So if this is somewhat not too small set, then we should be able to expect, we should be able to compute the, density between them, and that must be as expected. So for example, if you take a complete bipartite graph between them, then this is epsilon, this is epsilon regular for even epsilon, any epsilon. Because the density between A and B is 1, and whatever A prime and B prime we take, the density between them is again 1. So for any positive epsilon, we can, this is satisfied with t being 1. Also, if you have say n vertices here and n vertices here, and then you add an h between them with the probability say p. P is some number between 0 and 1, say. Then, when n is large enough, you can, prove that this random bipartite graph also is epsilon regular. Moreover, it's a epsilon p regular. Epsilon regular for, let's say epsilon regular for any epsilon. Yeah. It's not just epsilon, yeah, it is epsilon regular and also epsilon p regular for any, positive constant epsilon. As long as this n is much bigger than, say, this epsilon. So, maybe, so you need to get more used to this notation, this notion of epsilon regularity. I will, put some exercises on the lecture note or homework so that you can, get more familiar with this concept. And there are several reasons why this notion is so useful. So one of them is that essentially, it is useful because of this too. Any graph G for, say, for given epsilon, any graph G can be partitioned into not too many epsilon regular subgraph. And if you have epsilon regular subgraph, epsilon regular structure, let's say, whatever that means, we will see later. It helps us to find or even count the number of subgraph, number of specific subgraph. if you want to say find certain subgraph H inside of G, then roughly you can, decompose this G into many epsilon regular subgraphs, and then see how the decomposition gives certain structure, and then use that structure to actually find or count the number of H's inside of G. So this too provides us to some framework to find, certain subgraph H inside of G. So let's first, see what it means by that we can partition a graph into epsilon regular subgraph. For that, let's introduce some terminology. We say that a partition P of the vertices in G is an epsilon regular partition if so let's say this P consists of V1 to Vk. So we have, several vertex sets. Then we check whether each pairs are epsilon regular or not. And if the pairs which are not epsilon regular we take them and then we measure them. So we measure them by weight. If there are some small parts which are not epsilon regular, then we count small. But if there are big ones which are not epsilon regular, then we count small. So we count the multiplication of the size of 2. And then, we don't really care about some epsilon. Here, we don't really care much about the finding best epsilon, or epsilon or 2 epsilon or epsilon over 2 are not so much different for our purpose later. So we just count all the pairs ij from k squared. So we may count the same pair twice for ij and ji. Which also make changes up to some, multiplication of 2 or something. So as long as this is smaller than epsilon times the number of vertices in G square, then we say that this is epsilon regular partition. So meaning that if you have an epsilon regular partition, V1, V2, and so on, Vk, then it says is that many pairs are epsilon regular, and only small number of pairs are not epsilon regular. And then for those pairs, this contribution is small. It's only epsilon fraction of the, everything here. And the following lemma is called Semoredis regularity lemma. This captures, this phenomena. Any graph can be partitioned into not too many epsilon regular subgraphs. So what it says is that for given epsilon, positive number. So this is the parameter that we want. We want some epsilon regular. So this is the error parameter that we can tolerate. So this is our choice. And say t is our choice of number. Then we can always find, the following. So there is this integers say n. Give me a moment. Yeah, n might not be important. Let's say t such that the following holds. And every n vertex graph, every graph give me a moment. Every graph admits an epsilon regular partition B1 to BR with R at most T. So, okay, let's forget this T for now, small t. Yeah, I will explain it a bit later. So this T is actually, capital T depends on the epsilon. So what it means is that for whatever graph you are given, you can partition the vertex set so that most of the parts here are epsilon regular. Note that here, if the graph is small, then this doesn't really say much. If you have a small graph, then you can partition the graph into single vertices. Then every pair is epsilon regular. If there is an edge here, this is, epsilon 1 regular. And if there is no edge here, then this is epsilon 0 regular. So it doesn't really mean anything if graph is small. But if graph has much more edges than this T, then each vertex set must be, most of the vertex set must be big. And one of the, catch is that this bounds. We can find this partition, but the partition is, not much, partition itself is not a big deal because, as I just mentioned, if we just partition the vertices into singletons, then it's always epsilon regular partition for any positive epsilon. However, here is that we can actually find the one which is not too big. The number of parts is bounded. For any graph, we don't care how many vertices given this graph has. It could be much, much bigger than T, but still we can find this. And one of the good things is that this is small partition, and this small partition carries asymptotically same information about the original graph. Instead of, if you allow some error parameter, some error in the information that you want, then instead of dealing with the original graph, you can actually deal with this smaller graph and then get the almost same information up to certain error. So that's the philosophical interpretation of why this regularity lemma is important. Note that this T is some number that does not depend on, say, n, which is the number of vertices in the graph. But this is huge compared to epsilon, which actually makes this regularity lemma not so practical. So let's say tower of 1 is 2. Let's define this function. And tower of 2 is, tower of I plus 1 is tower of 2 to the tower of I. So tower of say 3 is the 2 to the 2 to the 2. So this I or this 3 measures the height of this tower function. So this is a function which grows very fast. And what we know is that this t is, can be taken as at most tower of epsilon to the negative 5. So which is actually a huge number. If you have epsilon to be say 1 over 10, then what's this? Some constant times. So this is like 10 to the 5, 100,000. That means you take this 100,000 times. That's the number of, number of sets in the partition, which is way more bigger than the number of atoms in the universe. So which kind of makes this regularity lemma not so practical. Anyway, so we have this summarized regularity lemma. And we can actually, add a few more conditions. So this regularity lemma actually implies that the more general version, we can actually, using that, we can actually prove this version of the regularity lemma. So for epsilon positive and t is any number, then there exists, t such that the following holds. Then every graph G has, admits an epsilon regular partition of partition, say B1 to BR, such that the R1 is that R is at least this little t and at most t. So we can ensure that sometimes this partition that we get, the number of parts might be small. So one thing I forgot to mention is that here we also count I, I. And if you have Vi and Vj, then that's not epsilon regular, so that's also counted here. So for example, if you just take, V1, when R is 1 and V1 is everything, then this never epsilon regular partition. So it kind of forbids that. And moreover, we can actually ensure that the number of parts is not too small. And we can also ensure that each Vi and each Vj have the almost same size. So we call such a partition as an equitable partition. If every set in the partition has a size, almost same. Difference is at most 1. And also, for each, the pair Vi, Vj is epsilon regular for all Ij in R square except at most epsilon R square pairs. So all pairs are epsilon regular except at most epsilon times r squared. We can even make it stronger. For each which is between 1 and r, the pair Bi, Bj is epsilon regular for all, say, inside of R, except at most epsilon R indices. Note that this R prime 3 is stronger than R3. So for each I, there are not many choices, at most epsilon R choices of J. Then you count all the pairs, then you get this. So we can even ensure this R3, R prime 3. So, roughly how we deduce this version from the version above is that, roughly I will explain it to you how we do. So this is what we want to get. Then we take, epsilon prime, say, which is much smaller than epsilon. We can take epsilon square or epsilon over 1000, and we apply this version of regularity lemma with epsilon prime. Not just that, let's just say this epsilon prime is smaller than epsilon and also much smaller than 1 over t. So depending on these two, we can find some function, and then we can actually express this in terms of these two. Then you find this partition, epsilon prime regular partition, which may not be equitable. So which could have many sets, small sets and large sets. And what we do is, if you have a large set, we partition it into sets of same size, and if there are some small parts remain, and small parts remain, then we collect. And if some set is so small, then we collect them. Let's say we have some number m. Every set with size bigger than m, we take a set of size m here, and then if some set has size smaller than m, then we collect. Then we can actually, after this, we can get each of set has size m, and size m, and we have, some sets, some vertices we have collected before. We can actually show that this has size smaller than certain number. So this collection is if every vertex is here, the number of vertices here is n. Okay, I think its time is a bit over, so maybe, yeah. I will resume the explanation in the next video. So, in the next video, I will, vaguely, roughly explain why we can, ensure these further conditions. But so far, what we have learned is that we have defined this concept of epsilon regularity, which says that somehow the edges are distributed in a uniform way. So edges here and here distribution and here distribution are somewhat similar. And Also, we learned that we define what it means to be a partition is epsilon regular partition. And then we introduce this summarized regularity lemma. If you have a graph, it always, you can always partition the vertices so that it admits a epsilon regular partition. And moreover, we can actually ensure more. We can ensure the number of parts being at least certain number, and it's bounded. And then we can ensure that the parts have the almost equal size. And then most of the pairs are epsilon regular. Moreover, we can ensure that each set is epsilon regular with the other sets for almost all of them except epsilon fraction. So we will, resume explanation about this in the next video, next lecture.